Okay, welcome back, Pre-Calc students. Day 2 of Unit 13 on derivatives, Intro to Calculus. Yesterday was all about average rate of change, slope of secant line. I put a couple warm-up problems up here for you. I'm not going to bother doing them. You know exactly what this should be. If I was going to find the average rate of change over the interval from 0 to 2, I'd be finding the slope of that secant line right there, which looks to me to be a negative, change in y over change in x. We also talked about average rate of change being an object's velocity. So of that function here, we can do it numerically. Find f of 0, find f of 5, change in y over change in x, and that would be the average velocity of that object over that interval of time. It would change constantly because it's a curve. Again, that's not a linear function, but the average would be a slope of a secant line. All right. But the question from yesterday was based on, what if we didn't have 2 points? What if we only had a single point? What if we were trying to find an instantaneous velocity? What would be on your dashboard when you were driving a car? At an specific instant, you're going a certain speed. So how do we find the slope of a tangent line is the question. Okay? So here's the approach we're going to take. Our average rate of change, or slope of secant line, is these 2 points, change in y over change in x. Very easy, okay? But what if the second point kept moving closer and closer to the first? In other words, that distance got smaller to that distance until the 2 points are almost right next to each other. That distance is almost negligible, or maybe it is 0. And then we would be finding, indeed, the slope of that tangent line. But the question is, how do we do that? Well, here's how, okay? We're going to take an arbitrary point xy. But instead of calling it xy, I'm going to call it x, f of x. Same thing. If you want to, call it xy, okay? Then we're going to add a small value, and we're going to call that value that we add h. So in other words, that distance that we add right there is h. So what's this point? This point would be x plus that h, y, which is f of x plus that h. Okay. So now, if we want to find the average rate of change, the slope of that secant line, we would say change in y. Let's do that. F of x plus h minus f of x over change in x. X plus h minus x. Okay? Well, what are we going to do? We're going to move that new point until it's almost sitting right on top of the first. In other words, the h is getting smaller. Okay? And then, as this second point, this f of x plus h point, gets closer and closer to the first, the line is getting closer and closer to a tangent. And what does that mean? The h gets smaller and smaller and smaller. Think about our most previous unit. As h approaches what? If it's getting smaller and smaller and smaller, it's a limit question, and h would approach 0. So if we put this all together, okay, this is going to be a really important tool. You're going to be sitting in your freshman calculus class, maybe with 50 people. You're going to get this concept. It's going to go right over their head. To change a secant line to a tangent line, we're going to take this x point, this first point, pardon me, x comma f of x. We're going to take this second point, x plus a little, f of x plus a little. We're going to find the average rate of change, change in y, over change in x. And we want that h value to get smaller and smaller and smaller, so we're going to write it like this. Pretty cool thing. One last thing we want to clean up. Look at that bottom. What's another value for x plus h minus x? And the answer is h. The h gets smaller and smaller and smaller. That is a very valuable equation. The fundamental concept behind introductory calculus, the limit definition of a derivative. The limit as h approaches 0 of f of x plus h minus f of x all over h. But you know what it means. It means you're finding 2 points to make an old school slope secant line. That second point is moving closer and closer to the first. So in the end, you're ending up with the slope of a tangent line, an instantaneous rate of change, instantaneous velocity. Okay? So that is our new tool in our toolbox right there. Limit. All right, so let's take another example using this whole idea. Give me a second here to clean up. There's our limit definition of derivative right there. We're going to do this a little more numerically, then we're going to move on to a more general type after. So, point P, 1 comma f of 1. Point Q, 1 plus a little. Oops, sorry. Yeah, red. F of 1 plus a little. So we want to end up, find the slope of that tangent line. So we're going to find the slope of the secant line from P to Q. We're going to slide Q back closer and closer to P. Okay? So what is f of 1? Well, that's red. So right there, 1 squared is 1, plus 1 is 2. So that point would really, whoops, sorry. Why didn't I do that in blue? So that would really be the point 1 comma 2. Okay? That's that second y. What is f of 1 plus h? Well, if I plugged in 1 plus h into that function, I would get 1 plus h squared plus 1. Then I FOILed that out. 1 plus h squared is 1 plus 2h plus h squared. I put it in standard form. Plus the other one minus the 2. So there's your red. There's your blue. Point Q minus point P. And we knew that the bottom cleaned up to just h. So what do I have? 1 plus 1 is 2. Minus the 2 cancel. And I'm left with h squared plus 2h over h, the limit as h approaches 0. And we know we always try to plug in, but if we did, we'd get 0 over 0. Can't do that. So instead we simplify. H, pull the h out. H plus 2 over h, cross out. And don't forget, that was just taking care of 1h. Now we've got to plug the 0 in for h, which gives us 2. What does 2 mean? What does 2 mean? 2 is the slope of that tangent line right there. But if I wanted to find it at another point P, maybe when x is 2, or when x is 7, or when x is negative 1, I'd have to go through all this work again because the slope constantly changes. There's another way we can be a little bit more generic. Okay, and that is we're just going to take 2 arbitrary points. xy and x plus a little y. The advantage will be that tool I can then use to find every different slope of a tangent line, not just the one that we found up here. So let's go through this a little bit. Okay? So f of x plus h minus f of x all over h, limit as h approaches 0. So I'm going to go back up to my function. 1 x squared plus 1. F of x plus h would be x plus h replacing the x. That's this one. F of x is just the function itself, whatever that might be. In this case, it's this. Again, I distribute that x plus h quantity squared. We're going to do that a lot of times, so remember what that is. X plus h squared equals x squared plus 2xh plus h squared. That's where that came from, plus this one minus that. Now if we distribute through the negative, I'm going to show you something that should look familiar from the unit review we did, and I said something about functions day that we would use it later on. X squared plus 2xh plus h squared plus 1, distribute through the negative, minus x squared minus 1 all over h. What happens? X squared minus x squared. 1 minus 1. Now I remember doing that. Leaves me with 2xh plus h squared all over h. Have to get rid of the h first, pull it out, they cancel. Limit as h approaches 0 of 2x plus h. We can now plug that in, is 2x. What's that? That is the tool we could use to find the slope of any tangent line to this curve. If I wanted to find the slope at 3, I would just say 2 times 3, the slope would be 6. If I want to find the slope at negative 2, 2 times negative 2, the slope would be negative 4. Let's be visual. Let's go up there. Negative 2 would be over here, and most certainly would be a negative slope. 3 would be here. Sure. So that tool of 2x becomes really valuable, but again, that 2x is the slope rule, that's the kind of term I like to use, only for this function right here. But it's for every point on that function. If it was a different function, we'd have to find a different derivative. That's the word we're going to use in a second, okay? But that 2x, real powerful for finding slopes of those tangent lines. So we're going to give that a name. We're going to call that f prime of x. That's the symbol. It's called the derivative of f of x. If I use the word derivative, that means you're finding the instantaneous rate of change, the slope of the tangent line, or if I said find f prime. In calc, they also use dy dx. We're not going to use that as much. So let's take this example right here. We have a quadratic function, 3x squared minus 2x plus 1. We want to find the slope of the tangent line. Immediately, I go to this tool in my toolbox. Limit as h approaches 0, f of x plus h minus f of x all over h. If I plug x plus h into the function, I would get 3 x plus h squared minus 2x plus h plus 1 minus the function itself, 3x squared minus 2x plus 1 all over h. Don't forget the limit. I almost did, as h approaches 0. We got to do a little bit of cleaning up. We don't have a lot of time to do it, so let's be efficient. We know what x plus h squared is. We're going to distribute through the 3. X squared times 3 is 3x squared. 2xh times 3 is plus 6xh. H squared times 3 is plus 3h squared. Let's distribute through the negative 2. Negative 2x, negative 2h plus 1. Let's distribute through the negative. Negative 3x squared plus 2x minus 1 all over h. A lot of things will cross out. 3x squared minus 3x squared minus 2x plus 1 minus 1. Leaves us with limit as h approaches 0 of 6xh plus 3h squared minus 2h all over h. Still couldn't plug in the 0 for h because I get a 0 on the bottom. Pull the h out. You've got to show each of these steps. h, 6x plus 3h, pardon me. Running out of time. I think we can make it. 3h minus 2. Cross those h's out. Limit as h approaches 0 of 6x plus 3h minus 2. There is no 0 on the bottom, so now I can plug in a 0 for h, and I'm left with 6x minus 2. That is f prime. That is the slope rule, the derivative of this one function only. And if I want to find it at 1, I just say f prime of 1